I wanted to welcome everyone to the presentation today on Structural Adhesives 101. My name is Steve Webb. I'm the presenter. I'm one of the senior application engineers here at Parker Lord, and I've got about 20 years of experience with these types of products. A little bit about what we're going to cover today. So we're basically going to start out by going over some of the terminology associated with adhesives and technical data sheets, give you a little bit of a background of what you're reading. We're going to talk a little bit about the structural adhesive chemistries that Parker Lord has to offer. We'll also cover types of bonding and some structural adhesive solutions. As you can see here, we can also join the conversation for tweeting on this webinar at Structural Adhesives 101, and certainly follow us at Lord Corporation on Twitter. So just as an introduction, we're going to start out here on talking about Lord Structural Adhesives, some of the product chemistry solutions, cure rates, capabilities, etc. Okay, how I'd like to start today is just talking about the terminology in general. This gives everyone a good background of what we're talking about, as well gives you the ability to kind of read a data sheet and understand what you're seeing. So the first two topics I want to talk about is adhesives versus sealants. Adhesives are materials that are designed to bond two surfaces or two materials together. Sealant is a little bit different. This is a material that may or may not bond to the surface well, but it's designed instead to seal out moisture, air, etc. from a seam or an assembly. It can be rigid or it can be an elastomeric, so high elongation material. It can be one component or two component. Most often in the industry, you'll see a one component material that's typically elastomeric. A good example of that would be caulk. Structural adhesive is a little bit different than a regular adhesive in that it's an adhesive which can achieve 1,000 psi or 6.9 megapascals in shear, or cause the substrate to fail when it's tested, or both when it's joining two materials together. That's a little bit different than an adhesive, because you can think of an adhesive as like an Elmer's glue, a contact cement. Those are designed to put materials together. But the difference of a structural adhesive is it achieves a certain strength value. The other two terms I'd like to talk about here briefly on this slide are two component versus one component. In the industry parlance, it's often referred to as a 2K material or a two component adhesive. And this is an adhesive that has two different materials that are separate, and when they're brought together, they will cure at a specific mix ratio. So when they're mixed at a specific ratio, the two products will cure. The one component material is an adhesive that just is a single part and is dispensed onto a product. And then once it's exposed to the environment, be that either moisture or heat, or even an energy source such as a UV cure or UV light, it will then affect a cure. On this slide, I'd like to talk about a little bit of terminology again, but in this time, I'd like to talk about some terms that are kind of used interchangeably in the adhesive industry. First one is open time or hot life or working time. So those three terms essentially mean the same thing. And this is the time allowable when the two parts are mixed up until the time the parts must be mated. Mating the parts after that expiration will typically result in poor bond strength. So that's how long you have to work with the material prior to getting the two parts assembled. Time is also listed on the data sheet, is also dependent on time and temperature and or mass of the adhesive. So typically adhesive manufacturers such as ourselves will say it's listed as a 1/4 inch bead at 70 degrees Fahrenheit. Know that with increased temperature, the material will typically cure faster. Decreased temperature will typically cure it slower. So from what's listed on the data sheet. The next term is kind of, again, a group of terms, handling strength or green strength or fixturing time of an adhesive. What this refers to is the time that's required for the adhesive to cure and attain sufficient strength to hold the parts together without additional fixture. Typically, that's in the industry of between 50 and 100 psi of shear strength. That allows you to move the part down the manufacturing line or move it out of the fixtures, and it won't debond. Time is typically also listed on the data sheet, but recall this is also dependent on time and temperature, adhesive mass, the joint design. So it's a general guideline, not an absolute. The third term I'd like to introduce is processing time. So this is the time required really for an adhesive to reach that structural strength when we're referring to structural adhesives. And that is 1,000 psi or 6.9 megapascals. Once the adhesive reaches that strength, the next step in the manufacturing operation can readily be performed without degrading the bond line or fracturing the part and causing quality issues. So things like cutting the part to length, adding screws or bosses or fittings, etc., painting the material, all those things require that it gets to a certain strength so that the joint is not debonded or disturbed when the next operation is being performed. Now I'd like to turn to a little bit on some of the terminology that really refer to the physical characteristics of the adhesive. Density and color being the first two. Density is just simply the mass per unit volume. It's commonly expressed as pounds per gallon or grams per cubic centimeter. And that's how much the material, in basic parlance, is how much it weighs, how much it's going to add to the assembly. Color is often listed in an uncured state and typically also as a cured state or even a mixed state. When two different materials come together, they might be different colors to create a third color when they're mixed. Flash point is the lowest temperature in which vapors from a volatile component in the adhesive will ignite when exposed to a small flame under controlled conditions. Oftentimes this is listed on the technical data sheet and also the safety data sheet. Many times this is what a manufacturer will use when they're considering bringing an adhesive in and where it would be situated in the plant, potentially next to welding sources or open flames or sparks. The mix ratio is for two component materials. It tells the ratio of one component to the other in the adhesive system. It can either be expressed as a by volume or by weight, oftentimes both. And when you see by volume, they're often a common mix ratio such as 1:1 or 2:1 or even a 10:1 ratio. So now I'd like to turn to some of the mechanical properties and you might see on a data sheet in regards to the adhesive terminology. These often refer just to the neat adhesive itself, not how well it's bonding to a particular substrate. The exception here being strength, and it talks about the maximum load or force that can be applied to the adhesive. It's a function of area acting over a certain part. So it's often expressed in pounds per square inch or megapascals per square millimeter. Elongation is just as simply the distance the material can stretch from its undeformed state until it begins to fail. It's usually expressed as a percentage, so something might have 100% elongation. A good example would be a caulk. It might have 200 or even 500% elongation. It's measured again on the neat adhesive itself, not as a bonded part, and it's extremely dependent on the test method. There are many test methods out there which will give different elongations. So it's something to be cognizant of. And if you have questions, certainly ask the adhesive supplier. Modulus, this is often listed and used from an engineering standpoint where customers can begin to design a part. It's just simply the relationship of stress versus the elongation. It's expressed in a force per unit area. And typically the higher the modulus, the lower the elongation. A few more mechanical properties just to discuss. Hardness, that's just how much or how strong a material is to resist indentation. It's typically done with a shore hardness tester, and it may either be on an A or a D scale. The A scale being a softer scale, the D scale being a harder scale. Coefficient of thermal expansion, or CTE, this is the relationship of the volume change and temperature for the adhesive. So like most materials, as the material gets warmer, it tends to expand, just like your metals or your plastics. And this gives the ability to begin to match those things up when you're designing joints that may be cross-bonding multiple materials, such as a metal to a plastic. Glass transition temperature, or TG, this is the temperature in which the adhesive changes from a rigid or glassy state to more of a rubbery state. Think of this more as like softening on thermoplastics. So it's a range of temperatures, not just an absolute. It's often expressed as a single temperature value, but know that the softening occurs over a range as a gradual process. The best example to think about is if you're thermoforming plastic parts, knowing that the material will begin to sag or begin to reach that rubbery state at one point of temperature, and when it's finally used, it may have to reach a second temperature where it's more elastomeric, more stretchy to do the vacuum form. Okay, now that we have a little bit of a background on some of the terms you might see on a technical data sheet to begin to understand how an adhesive works, I'd like to talk to you a little bit more now about Lord structural adhesives and some of the chemistries we offer, acrylics, urethanes, epoxies, as well as some of the packaging materials, cartridges or convenience packaging. You can see that in the picture here to the right. Bulk packaging being pails and drums and gallon kits, and then the convenience packaging being cartridges of material that can be readily dispensed on your application. Many of our products offer multiple cure speeds, so they have a consistent adhesion and consistent physical properties across a wide range of different open times. So we may offer a 3 to 5 minute open time for a faster product, and maybe a 60-minute open time for a slower product. Glass bead technology is something we offer in some of our products. This helps maintain the optimum bond line thickness with adhesive and prevents too much adhesive from being squeezed out. As I said, I'd like to discuss a little bit more about the Parker Lord adhesives that we offer. So these are just a general overview of the different categories of adhesive, and then I'll get into the specifics of the products that we offer under each of those chemistries in the subsequent slides. So starting out on the left here, we've got acrylic products. These are often two-component material, or 2K as we've said. They're designed really for bonding unprepared metals and also cross-bonding to other materials such as plastics and ceramics. They typically require minimal surface preparation, bonding to light oily metals. So typically a dry rag wipe is all that's necessary. And it's a room temperature curing product. So when the two components are mixed, it'll cure at room temperature at a set speed. Urethanes, again, two components quite often, designed to bond plastics, foams, primed or painted metals, composites, etc. They tend to be quite flexible, have a lower odor than the acrylic products, and again, a room temperature cure. The epoxies, they offer the ability to bond certainly prepared metals, foam, fiberglass, composites, wood, metal, ceramics, etc. They have some of the highest shear strength and typically some of the lowest elongation. However, they do offer the best environmental resistance, so to acids, bases, water, fuel, etc. And again, room temperature curing products. The MS polymer is kind of a newer category for us. These are designed also to bond unprepared metals, painted surfaces, composites. They have a high elongation, so typically greater than 100% elongation, and often we use them as a sealant or a sealant/adhesive. These products can achieve over 1,000 psi in shear strength in some cases, depending on the joint design, but typically they're used as a sealant. One unique feature about them, and I'll talk about later, is that they are paintable immediately with wet paint systems. They don't require skinning over first. So that's just kind of a broad overview of our different two-component chemistries. Again, all of them can be cured at room temperature. Many manufacturers use heat to accelerate the cure, such as the automotive industry or different composites industry, where they might be using heated tooling or painting operations. We have this wide range of chemistry, and the adhesives are designed, and we test all of them to maintain their strength and adhesion after long-term exposure. So we look at multiple types of environments, cyclic fatigue, salt fog, humidity, thermal cycling, various chemical exposures, etc., to help understand how well these materials perform long-term. At this time, we go ahead and launch our first poll question. And just take a couple minutes to answer what kind of adhesive you're currently using or even currently considering. Okay, now we're going to talk in more specifics about the individual chemistries and some of the product offerings. This first slide we're going to look at is acrylic adhesives. Starting on the left, we're going to start with the MaxLock family. This is kind of our go-to product. It's one of the best performing metal bonders we have. It is a family, so it has a range of open times, very high shear strength and high peel strengths. It's resistant to high temperature bakes, such as an E-coat or even a powder coating. And again, low surface type product. 400 series, another workhorse product, has a range of open times, excellent shear strength and peel resistance, and it has a really long proven track record of performance out there in the marketplace. It's resistant to oven temperature, high temperature bakes such as E-coat, but is not the best for powder coating operations. The 600 series is a more specially designed product, really designed to bond composites and plastics and cross-bond to metal. We also offer in that family some very long open time versions, upwards of 60 minutes. The 850 is one of our newest, so going all the way over to the right, has a couple of different products in that family. It's kind of a go-to product for new high fatigue applications, so where you would expect to see higher fatigue on the metals or the composites, this is one of the excellent choice for that. It has excellent shear and some of the highest peel strengths, very good elongation for a structural adhesive, high elongation over 100%, and one of the best performing on stainless steel and hot dip galvanized metals. Again, all designed to bond metals or cross bond, other different types of metals or even composites, engineering thermoplastics, and then typically with our customer support, we will offer testing on their applications and their materials in order to help engineer a solution in for the specific customer. Okay, I'd like to now turn to the urethane adhesives. Starting out again on the left-hand side of the slide, the 7545, this is kind of our go-to urethane family. Has the broadest range of open times. It's a really good choice for engineering thermoplastics and composites. As like all the other urethanes, it has a very low odor, and it's good for cross-bonding these different materials together. The 7800 series, moving over, this has the fastest cure rate of all the urethanes. It's very similar to an acrylic on how fast it cures. It has one of the highest elongations as well. However, it does have available members of that family, so less selection in terms of open times, but it's certainly good for replacing heat curing urethanes that might be out there on the marketplace, such as where you might have heated tooling. The 7542, this is a workhorse product in our urethane family. It's a gravity feed, so it offers lower cost of implementation with respect to capital purchase. You don't need transfer pumps to pump the material when it's used in bulk. It does have a high elongation and good for cross bonding. Lastly, I'd like to talk about there's a couple of specialty products in our 1 component or 1K urethanes, 74 and 11 and 12. This is a reactive hot melt like type material designed for bonding TPU or thermoplastic urethanes and hoses. It is those two products are 100% solids. 7433, that's a pourable version of the material, again, bonding for TPU, rubber, and hose bonding. It is 100% solids, so in that case, the explanation is there's no additional solvent carrier. The difference here is the 7420 and 21, these are pourable materials, but they do have a solvent carrier with them that can help with improving adhesion, but it does force you to evaporate that solvent prior to the bonding hose and overwrapping, etc. So that's just a brief overview of the urethanes. Again, all designed for bonding painted metals or prepared metals, plastics, composites, and foams. Urethanes are typically a good choice for composites and plastic bonding, where the temperature and environmental conditions are not quite as extreme maybe as needed for an acrylic or an epoxy. So typically operating temperatures of 250 degrees Fahrenheit or less, 121 Celsius, and neither highly acidic nor highly basic in nature. Okay, now we're going to turn to the epoxy adhesives. For the epoxy adhesives, we don't necessarily have a family of go-to products. There's just a lot of different products in this category, and so I'll just briefly touch base on them. We have a metal-filled paste with the 304, good for MRO operations, etc. A syrupy type product for general composite bonding and foam bonding with the 305. The 310 and the 320 are probably the closest we have to workhorse products. 30 to 60 minute open time for the 310, or working time of the product. Very high strength, very high performing epoxy. And then the 320 is a toughened epoxy where you might have more slam, impact, fatigue, cold resistance needed. And again, a 20 to 40 minute open time or working time of that product. We have some 5-minute epoxies with the 360 and the 363. 360 is a paste-like material, 363 is more self-leveling. Certainly good for bonding studs into concrete, brick, cinder block, etc. The two next categories are more specialty products. With the specialty products specifically, we have some cryogenic epoxies designed to operate at very low temperatures, minus 100 Celsius, minus 200 Celsius temperature range. That's the 3170 and 3135. We have a NSF certified epoxy, that's National Sanitary Foundation, where it would come in direct contact with potable water. That's the 305/307. A NAVC mil-spec product with the 306. Higher elongation epoxies, so atypical for epoxies where you see 50% or 70% elongation. That's with the 312 or the 340. And we also have a traffic marker epoxy designed to bond down traffic markers into the roadbed themselves with ES116. So with the aerospace epoxies, we have for bonding aerospace composites and metals together, we have the 309, 3135, and 4952. The 4952 is certified FST, or flame, smoke, and toxicity, to the FAR 25853 regulation, or the Federal Aviation Regulation. We have a couple of syntactic foams with 1110, 2850, 4688, and 4719. And then certainly we also have some insert potting materials. Again, all the epoxies do well with room temperature curing. They'll perform better when heat cured. All the epoxies certainly cure at room temperature. That's what they're designed to do as a 2-component material, but they will certainly perform better when heat cured. The heat improves the strength and the chemical resistance and the glass transition temperature, or TG, of the epoxies. Epoxies are really good choices for composites such as carbon fiber reinforced plastics or CFRP, thermoplastics, and anywhere where the temperature and environmental conditions really get above 250 degrees Fahrenheit, or highly acidic, a lot of fuel exposure, basic conditions, etc. So on this slide, I want to just briefly illustrate some of the cure rates of a product. This helps in the consideration of when selecting an adhesive. One of the things that makes an acrylic unique, as you can see here in red on the slide, is that it cures very, very fast once the working time or the open time is expired. So it develops strength quickly, and it reaches that structural strength or processing strength where you can do the next stage in your manufacturing operations. That's really one of the true advantages of an acrylic, aside from being a metal bonder itself. Urethanes and epoxies, these are typically slower. They're a linear cure rate. You can see they slowly reach their full strength. And this is why many manufacturers decide to apply heat to these products during their manufacturing operations to accelerate the rate of cure. So as we talked about a little bit on some of the adhesives that we offer, some of our process and solutions that we offer on this slide I wanted to briefly discuss. So when we want to assemble a product with adhesives, we start out by selecting an adhesive, and then we will decide whether it's needed to be dispensed via MMD or mixed metering and dispense for bulk applications or for cartridges. We'll help the customers with processing and fixturing design. So how can we really implement this? Maybe a great engineering solution, but how do we get it into manufacturing? And that's one of the key things that we offer into a customer. As well, if earlier in the design process, if they're looking for joint design, we can certainly help the customers with that, helping push them in a certain way or redesigning a joint to better accommodate the use of adhesives. So now we've kind of talked about a little bit on the applications and the products that Lord might offer, the adhesive systems. I'd like to talk now a little bit about common bonding applications, be they either metal or composite, plastic, and maybe even some natural substrates. So in this first slide, I'm going to talk a little bit about metal bonding. Lord Corporation helped design some of the first chemistries to bond metal, and we think we've offered some very good solutions to the industry. So here's kind of an example here where we're replacing typical conventional joining methods such as welding or mechanical fastening. So in this first slide, I'd like to talk a little bit about metal bonding. Lord Corporation helped design and implement some of the very first solutions for bonding metals with adhesives. And what we've come to do is really replace conventional joining methods such as welding or mechanical fastening, rivets, screws, etc., where the structural adhesives offer performance improvements in terms of cost or aesthetics. And certainly the performance improvements are a big category as well. You can see here on this slide just a brief example of bonding to 6061 T6 aluminum, some of the different products such as the 850 series, the MaxLock, the 400 series. And then we're looking at it here versus a competitive adhesive where we've exposed it with temperature and time, and we can see that the competitive product degrades, whereas the Lord products do not. So when we talk about metal bonding and some of the adhesives out there, a lot of times we'll see a lot of different common materials that we're very accustomed with. So the aluminums, the steels, maybe a common steel or a stainless steel, like a galvanized or galvanneal, galvalume, galfan, those are some of the trade names. We might see painted metals such as powder coated, electrocoated, or even a wash coat on aluminum. Conversion coatings such as anodized, phosphated, or chromate conversion coatings. Some of the less common ones we might see are magnesium, titanium, cast iron, bronze, brass, copper, etc. We certainly work with those and have solutions to those, but this is just a good idea on some of the materials that we've worked with in the past. So just a basic idea on how to select a metal bonding adhesive with this slide. We want to talk about that just a little bit. The condition of the material that we're starting with, where we would choose which adhesive, and then maybe some comments on it. So unprepared metal, for the basic as received metals materials, we select the metal bonding acrylic. That's primarily what we're going to do with all of these. Whether it's corroded, then we would ask that the corrosion be removed. You can't make a good bond if you're bonding to a corroded surface such as rust or the oxides that form on aluminum. Bare metals to fiberglass or FRP, we'd certainly select the metal bonding acrylic, and then we'd test the adhesion on how well it performs to the FRP. Bare and coated metals, again, metal bonding acrylic and testing the adhesion. Again, something that Lord Corporation offers. Bare metals to wood, we've seen those. We'd probably go with those cases either a urethane or possibly an epoxy, and we prime the metal and then test adhesion. galvanized metals. We talked a little about those. Certainly metal bonding acrylics, and then very high or low temperatures. We first select probably the MaxLock series because it has that highest temperature resistance of the metal bonding acrylics. Now that we talked a bit about the adhesives and the chemistries and how we'd select one, just some common applications that we perform within the industry. So for industrial assembly, we certainly work heavily in the trailer and transit and utility bodies markets where we're bonding roofs and doors and walls and floor panels, underbody boxes, truck beds, etc., lift gates, and then certainly some bracketry and hatches and shelf hangers are some very common applications. We work with heavy-duty truck, RV, service work trucks. We work with containers, shipping containers, HVAC, sign. In the military aerospace, certainly fixed wing and rotary wing aircraft, missile components, armor bonding applications, general industrial, agricultural machinery, satellite dishes or antennas or dishes, speaker assemblies, and construction such as windows and doors and other architectural cladding products. On this slide, I'd just like to highlight some of the specifics of maybe some metal bonding or cross bonding applications. An example here we'll use a bus. Certainly where you're bonding a roof on, it might be either composite or metal. Door bonding, quite often a metal to a metal frame, so panel on frame type applications. The same thing would go for the side panel bonding with luggage doors, where you're bonding a metal sheet onto a frame or other structure. Certainly there are other applications and we offer adhesives for doing those, but I just wanted to highlight a few on the metal bonding applications on bus. Recreational marine vehicles, certainly there are metal bonding applications on these as well as composite or cross bonding applications. So our adhesives that we supply to the industry have that ability to bond to dissimilar materials and join them together. High performance two-component adhesives and sealants for these types of applications, and certainly high adhesion and durability. This kind of leads to that longer service life of these products. Another one here is examples and highlighting specific areas of work truck bonding. So the box that's put on the back of a truck where they might assemble it. There's certainly sidewalls where you've got a sheet on post design or a composite sidewall where it's a metal composite. The upper roof rails or roof bonding structures themselves, and then doors and enclosures on the back of the truck or maybe on the side of the truck body. So just to highlight a few on metal bonding of emergency vehicles. This is a market that's come quite a ways on replacing welding. Typically these are aluminum type structures built as a box for an ambulance or even a fire truck. And we have quite a few applications where you can bond sidewalls where it's an extrusion to a panel. Roof bonding, again, the same thing. Panel bonding on the inside of the vehicle, HVAC bonding, and also doors and closures. Last one, certainly with emergency vehicles, is bonding on aluminum diamond plate for decorative elements. On this slide, I'd like to highlight some metal bonding, more specialty construction applications. We have specialty acrylic metal bonders and other products that are into this industry that are used. You'll see things like window mount bonding and this for sealant and sealing applications, panel to frame for this architectural cladding you can see on the outside of the building, sealant applications, and basic construction for architectural elements such as column wraps or columns themselves. Moving away from metal bonding, I'll talk a little bit more about composites. These oftentimes do include some metallic elements. So we offer adhesives that replace joining methods such as tabbing or mechanical fastening these structural elements together, such as insert potting, but certainly the bonding the structural composites themselves together with either a urethane, an epoxy, or an acrylic adhesive. And just some examples of it, you might see aluminum composite material quite often used now in heavy-duty truck and truck applications. So just to briefly highlight some of the materials here, some of the primary adhesives we might use are urethanes or epoxies or even acrylic adhesives on these. The first one here is the aluminum composite material, often used in heavy-duty truck and truck construction itself, as well as architectural cladding. Honeycomb elements that you more often see in aerospace, and then certainly with the Nomex and honeycomb core, more often used specifically to aerospace. Some of the common substrates we see in composite bonding, certainly the more general ubiquitous category is fiber reinforced plastic. And this is either a chopped or woven material reinforced by polyester or epoxy or vinyl ester resin matrix. This can be sprayed or compression molded into sheets. The gel coat is typically what's applied to the mold side of the product. gives it its bright, oftentimes a bright white or shiny surface. Composite foams to help reinforce and lighten the composites. Closed cell forms, typically urethane. Good example would be Kusa board or Penske board composite sheets. And then more advanced composites where the reinforcing material might be like a carbon fiber or a Kevlar woven matrix or an S-glass or an E-glass that's then reinforced either by an epoxy or a vinyl ester. Those high performance matrices typically would look at epoxies and other types of products going into them and bonding them together. So when we're selecting an adhesive, I've touched on it briefly on the previous slides. We just look at the materials themselves and how they're bonded and then which adhesives we would choose, and then potentially some comments on what we want to do. FRP, we typically recommend either an acrylic or a urethane due to the faster cure rates of those two products. Certainly an epoxy can be used. You oftentimes end up grinding the surface of the FRP if it's a urethane or using a release material itself to prepare the surface. Fiberglass to plastics or FRP to plastics, again, urethanes and acrylics, and many of these things will test the adhesion along the way. The FRP to plastics is an example. FRP cross-bonded to metals, again, testing the adhesion of the individual assemblies. To coated metals, the same thing. Wood, typically on those we wouldn't use an acrylic, we might use a urethane, possibly an epoxy. FRP to masonry, again, an epoxy or urethane depending on the conditions that it would go into. And then FRP just to itself may or may not need to prepare the surface, but typically in the urethane or acrylic solution. In this slide, I'd like to talk just a little bit about plastic bonding and kind of just some general terminology and more information. Plastics come in a plethora of solutions. Many of them are blended nowadays. They often are bonded only by a specific adhesive or a type adhesive. The plastics may be the same type or the same general category, such as acrylic, but when supplied by different vendors, they may bond completely differently. This is usually differences due to the mold releases and the plasticizers, so it may still be categorized as an acrylic plastic or a polycarbonate plastic, but it may perform differently. That's why we often recommend doing some additional testing to ensure that the materials that you're selecting, that the adhesive bonds to those specific plastics. And some plastics, such as low surface energy, a little bit of slide on the right, that's just how well the material wets out. You can think of it as a car that's not been waxed or one that's been freshly waxed. On a freshly waxed one, the water will bead up, and the same is true when an adhesive is applied to a low surface energy plastic, such as a polypropylene or polyethylene. The adhesives don't wet out well, and so they're ones that need additional surface treatment. As a general rule, the same thing applies for any cross-bonding to metal, and plastics generally applies. That when we're bonding those two, use a metal bonding acrylic adhesive to bond to the metal and test adhesion to the plastic. Just some common substrates that we want to discuss out there for plastic bonding. As you can see, there's a plethora of materials out there. There's the thermoplastic materials such as nylon and PET, ABS, PVC, polyethylene, polypropylene, polyphenylene oxide, PPO, etc. PMMA or acrylic, polycyclopentadiene, PC, PD, acetal, PPS, etc. And then from those, there are an enormous number of blends of the materials, such as polycarbonate, ABS, etc. And then there's thermoset plastics, such as PEI and polyurethane materials. So a wide variety of materials out there in the plastic industry. I highly recommend that you talk to a technical service person or customer service person to help out with selecting the right adhesive for the right plastic, and then probably do some additional testing as well. On this slide, just to those common substrates and common applications out there, you can see the plastics might be used in transportation, such as the covers or air dams for trucks. Certainly some of the materials that are thermoset plastics are used on hoods for heavy duty trucks, corner caps, trim, etc. Sporting equipment such as canoes and kayaks and golf clubs. Architectural products such as the windows and door frames or rigid foam columns going around architectural trim. Office furniture, shelves and seats, and certainly injection molded plastic parts such as in the appliance industry or display cases or even toys. So in this slide, I just briefly talk about which adhesive we might select. I won't go through all of them, but generally speaking, the adhesives, we can often use multiple chemistries, and it Testing will oftentimes reveal the best adhesive for the application or the amount of processing time required for the individual assembly. So the PMMA or acrylic materials, those acrylic adhesives or urethanes work well. PVC, again, urethanes and acrylics. PEIs, urethanes possibly in epoxy. ABS, certainly acrylics and urethanes. Again, the list goes on. I would certainly suggest that you contact a Lord customer service or technical service representative to help out with selecting the correct adhesive for the correct application and how surface treatments might need to be applied. At this time, we're going to go ahead and launch our next poll question. I had an opportunity to see some of the different adhesives chemistries we offer, as well as some of the different materials that we bond to. We'd like you to just take a moment and consider that. Natural substrates, just a little brief on this, briefly explain just these are the materials that you might see as masonry, not exactly a natural one, but we categorize it because it falls under stone, so concrete, brick, or stone. These epoxy adhesives are oftentimes the best choice, as many times these things are exposed to the environment, and epoxies have one of the greatest environmental resistance out there. Wood, if you're bonding to other materials, so cross-bonding those, lumber, plywood, pressure-treated materials, urethanes made excellent choices. Acrylics are not so much, although they do offer a faster cure rate. They have some reactions with wood where they may not bond as well. Ceramics, certainly epoxy and urethanes adhesives. When you get into more specialty ceramics such as armor bonding, then we typically recommend an acrylic adhesive. On this next slide, we're just going to briefly touch base on elastomeric materials. Like plastics, there's a ton of materials out there. We offer different adhesives for bonding these materials. Adhesives for industrial assembly are typically an epoxy or a urethane type product, bonding to things like SBR rubber or styrene butadiene, EPDM, nitrile, fluoroelastomers, polybutadiene or butadiene rubber, isoprene rubber, etc. On all those, we will typically also recommend surface treatment, such as a primer for the materials. And if these are strictly for bonding materials that have been completely vulcanized or cured to another material or to themselves. In areas where we're bonding in a mold or in a forming operation, that falls more under our ChemLock line. We'd highly recommend contacting a customer service representative to discuss ChemLock options for those types of applications. So this one, just a brief overview of some adhesive testing. These are some things that adhesive manufacturers will test, and we've talked about a little bit or touch base of them along the way. This is just a kind of a brief explanation of how those tests occurred so that you gain a better understanding of the information on a data sheet. So lap shear or shear strength of an adhesive. This is the first example where two coupons are bonded together with certain size of the overlap and then pulled apart in shear, and the strength of failure is measured. T-peel, as you can see here in the next example, it looks like the letter T, and so it's pulled apart in shear, but it begins to form a peeling operation, and so you get a measurement of how well the adhesive both adheres to the substrate, but what its peel strength is. The fixed base is typically a tension pull-off, or an adhesive is tested in tension. These are typically with rigid substrates where they won't go into peel or mixed mode. And then another one that's often cited on adhesive manufacturers are cold impact. This is where we make a shear sample and then impact it with a weighted pendulum from the side. Quite often in the automotive industry, it's done at -40 Fahrenheit, -40 Celsius, and it's struck from the side to see how well the material resists impact at very low temperatures. At this time, we'd like to launch our final poll question. And this is really just on testing. Do you currently test your adhesives or your assemblies, or is this something you'd like Lord to work with you on testing your assemblies? This slide, I want to highlight a few things. We've talked about throughout about replacing welds and mechanical fasteners with an adhesive. So this is just a brief example of testing the material, the adhesives side by side with a spot weld on 6061 aluminum. And you can see here, the adhesive by itself on a continuous bond performs very well. About 5,000 pounds of force to pull apart the sample. I believe these were 4-inch wide samples. When you compare that to spot welds on either 1 or 2-inch centers, the next two columns, you can see it drops off significantly, or even 3-inch. It's really only when you get to MIG welding on 1-inch centers do you get an equivalency to adhesive. It certainly drops off as you space the welds out further. As we mentioned, at least a couple of slides in here, that we would offer testing and joint design to the customers and offering different applications on how to optimize for adhesive. This slide gives a good example of why we want to do that. So you can see here that the adhesive alone and the design is critical to performance, where the adhesive does a very good job, just over 2,000 pounds of force when tested, but the spot welds do a much better job on this particular configuration. Again, where it might go into mixed mode, starting out in shear, then in tension, and also some peel forces being applied. It's only when you get to 2-inch or 3-inch centers that the adhesive outperforms those types of welds. And that's really just to finish it up. I'd like to thank everyone for taking their time out of their day to hear my presentation and learn a little bit more about structural adhesives. Again, my name's Steve Webb, one of the application engineers. And if you'd like more information, you can certainly email or call us at 1-877-ASK-LORD. My email is stephen.webb@parker.com.